Good. Good. Yeah. What about you?
Okay. I'm like, I don't know, like, I just need to feel
This one might be of interest to you.
yeah. Are you?
Yeah, definitely. Did you hear back from the or no?
No, I haven't heard back.
Okay.
I've seen it.
Definitely matches it. No problem. It's fun.
Okay, so it's a great pleasure to introduce Zixia Wei, who's visiting from Harvard. So Zixia did his PhD with Tadashi Takanagi of RT formula fame, and he's thought deeply about gravity and computation. So, Zixia.
Thank you so much. Thank you much for the introduction, and thank you also for the invitation. Today I'm going to talk about informational and computational aspects of holography, and different from many talks, most of the talks in this conference. Today, this talk is going to be a review of some major ideas in our community where we use something called holography to study the physics of quantum gravity. I will mainly focus on some quantum informational and quantum computational aspects of this object, and I hope there might be, I hope there can be like an interactive conversation between people from different fields. So I understand that the language I'm going to use could be pretty different from the language used by the audience here in this conference. So please do interrupt me at any point if you have any question. Okay, so first of all, what is holography, and why should we even care about that? So here by we, actually I mean both computer scientists and physicists. So it is very well known that the interplay between the computer science and physics can benefit both of the fields. Here I just listed out two very recent examples. So the first example listed here is that the no low energy trivial states theorem is a very important theorem in the quantum computational complexity theory. And it was recently proven by these people. And in that proof, the intuition from quantum many-body physics actually plays a very important role. So that can be regarded as an example where the theoretical physics leads to a contribution in computer science. On the other hand, there is a very interesting result found by these people. I think all of them, they are computer scientists, that if you think about a quantum many-body system and talk about the so-called Gibbs state, which describes the finite temperature physics of this kind of system, then you will actually find that there exists a threshold above which there's no quantum entanglement at all. So this result is very, very surprising to physicists, and it has a very great impact on the physics community. However, it wouldn't be found if without the insights from computer scientists. And here I also list out a very canonical old example, which is now this conference we talk about quantum computation. And in fact, the very first sketch of building a quantum computer given by Feynman back in 1981 was motivated using such a computer to simulate the real-world physics, which was expected to be described by quantum mechanics. Okay, so given all these examples, let's make a very simple but somehow obvious statement, which is the computer itself, it should be built on physical reality, and in turn, it helps us learn about the physics itself. That's exactly what we experience every day. Okay, so given such a situation, it is very interesting to notice that so far, gravity is a physical reality which we experience every day, but this physical reality has not yet been used in any existing computational models. So one idea is that maybe we can build a computer based on the physics describing the quantum gravity. This kind of idea was firstly proposed in this paper. So that sounds like a very, very great idea. However, even nowadays, we don't really have a very good theory of quantum gravity to describe all the phenomena we are observing in the universe. While this quantum gravity is still under exploration, the so-called holographic principle plays a very important role in the exploration of the quantum gravity. So let me just very briefly write down the statements of the holographic principle. So in the holographic principle, we think that a theory of quantum gravity living in a d+1 dimensional spacetime is actually equivalent to quantum mechanics, just standard quantum mechanics, without any gravity, which lives on the boundary of the above spacetime. So in our case, we know that our universe is probably 3+1 dimensional, as long as there's no extra dimension. If we apply this holographic principle in our universe, that would be described by some 2+1 dimensional quantum mechanics without any gravity involved in that. Okay, so this looks like a very bold statement, but let's just once accept that. Then after accepting this statement, we will say that the mysterious quantum gravity is actually related to well-understood quantum mechanics. And this kind of relation makes holography a very powerful tool for exploring the theory of quantum gravity. So today I'm going to focus on this holographic approach of quantum gravity. And actually, in the past decades, this field has been greatly promoted by theoretical tools from both quantum information as well as quantum computation. On the other hand, it also gives new inputs to the study of the QIQC. So in the following, I will review some informational and computational aspects of this holographic principle. I will mainly focus on a specific example of holographic principle called the ADS-CFT correspondence. And I will mainly focus on the entanglement structure in this kind of theory. So using quantum information and quantum computation to study ADS-CFT is a very, very broad field. I'm sorry that I cannot mention all the wonderful works, but just to a very, very narrow discipline of that. So let us, before talking about quantum gravity, let us firstly review what a classical gravity is. So when we were kids back in the schools, we learned from the textbook that the Newton describes gravity as some force which attracts objects between each other. And that kind of gravity theory worked very well before early 20th century. So in early 20th century, Einstein proposed a refinement of the gravity theory, where he identified the gravity as the space-time geometry itself. So, for example, in our universe, we live in a 3+1 dimensional space-time, and this space-time is not actually flat; it's curved in some sense, and the curvature of the space-time is determined by the matter contents in the space-time. So, for example, like in this picture, if you have a very, very heavy object here, the heavy object will result in a curvature in the space-time. On the other hand, matter itself also moves in the space-time. So it's a kind of feel the gravitational effect coming from the other object. And in that way, there is an interplay between matter and space-time geometry, and that turns out to be the gravitational force in this kind of description. Okay, so that is our current understanding of classical gravity, which is nothing but just space-time geometry. So if we want to uplift that to a quantum gravitational theory, although we don't know what exactly that is, that must include some essential components. Some of them are the fluctuation of the space-time geometry, and some of them are superposition of the space-time geometry. There are many approaches, and today we are going to focus on holography, which states in this way. So let us focus on a very, very specific example of the holographic principle, which is called the ADI-CFT correspondence. So the ADI-CFT correspondence states that if we consider a quantum gravitational theory in d+1 dimensional asymptotically anti-de Sitter spacetime, that should be equivalent to a d-dimensional, one-dimensional lower conformal field theory living on its boundary. Yeah, please.
For a previous slide, is there a well-defined mathematical formalization of space-time superposition fluctuation?
Yes. So maybe let me say it in this way. So we have a formal mathematical formulation of that, but that is not a very rigorous one because we cannot really do computation using that formalism. So it's like you can write that kind of stuff as a functional integral, but that functional integral involves continuously infinite many degrees of freedom, where we don't really have a tool to carry that computation. So it's like something like that. Like we have the formalism, but we don't really know how to do the computation.
But then how, we believe that this is the right formalism to capture quantum.
Yeah, so although we cannot really perform the full computation from that formalism, we can certainly look at certain limited regimes of that formalism. And in those different limited regimes, this kind of computation can be reduced to some doable computations, where we can do some computations in those limited regimes, and then compare that with daily observations and some other things. So it's not like we have a formal theory for which we don't really know how to compute, but in certain regimes we can compute, and you can use that computation to match with experiments and some other things. Thank you for the question. Okay, so now this ADI-CFT correspondence focus on a very, very specific kind of space-time and a very, very specific quantum mechanics. for simplicity in the following, we consider the case where D is equal to 2, by which we mean the de Sitter spacetime itself is 2 plus 1 dimension, and the quantum mechanics itself is defined on 1 plus 1 dimension. So here I show a figure of a time slice of the 2 plus 1 dimensional ADS. So a time slice of the 2 plus 1 dimensional ADS is nothing but a hyperbolic surface. A hyperbolic surface is, it's just the analog of a sphere, but in a hyperbolic way. And a hyperbolic surface can be written down using the so-called Poincare disk representation, where if you look at this figure, this shows a triangulation of the hyperbolic surface. And each triangle appearing here, they're all identical to each other. So in this representation, if you look at the center and move from the center to the boundary, then the volume becomes larger and larger, and it actually grows exponentially. And CFT is a very, very specific quantum mechanics, but here we don't really want to dive into that. It's sufficient to understand that as some quantum memory system. Okay, so we formally state in this way, but in what sense they correspond to each other? Let us firstly consider a 1 plus 1 dimensional CFT, which is defined on a circle. So it's a one-dimensional quantum memory system. Then we can pick up a quantum state from the Hilbert space of the CFT. And on the ADS set, it can be described by either of the three choices. So the first choice is that because the ADS is gravity, and gravity is a theory of geometry, it firstly corresponds to some geometry whose boundary is nothing but the circle on which the CFT is defined on. And on the geometry M itself, you can again consider a quantum theory and define a quantum state on that geometry. So in this case, a quantum state in CFT is described by a combination between a geometry on the ADS side and a quantum state living on that geometry. So that's the first choice. The second choice is that, of course, we can take the superposition of this kind of stuff, and that gives the second choice. Logically, there's also a possibility that there might exist some state which is described by neither of them. But so far, there's no proof that such a kind of thing actually exists. Okay, so in the following, let us focus on the first class of states. So because this first class of states is described by a single geometry with a quantum state defined on that, let us call this a geometric state. The primary example of the geometric state would be you think about your CFT defined on a circle. Then, of course, that CFT has a ground state, which is the state which has the lowest energy. And the corresponding geometry of that ground state is nothing but just the hyperbolic surface with, again, another bulk ground state, which is defined on this hyperbolic surface. This is approximately the case, but not exactly true, but we can regard it in this way. There are also some other examples. Another canonical example is that if you think about the canonical Gibbs state in CFT, which describes the finite temperature state in the manifold system, that actually turns out to be a black hole in the ADS spacetime.
Sorry,
yeah, please.
Question. Where is the notion of energy on the hyperbolic surface?
Oh, yeah. So here, what you do is that you have a hyperbolic surface. And on the hyperbolic surface, you define another quantum theory. So you can think about, like, so here you actually have two quantum theories. One is a quantum theory on the CFT, on a circle, and that is the CFT. And then you have like a 2D geometry. And on that 2D geometry, you have another Hamiltonian, using which you can define another notion of energy.
So if I knew the conformal field theory, it sort of prescribed how to get this Hamiltonian on the hyperbolic surface?
Yes, that's a part of the ADS-CFT correspondence. Like you actually have a way to like you're given a CFT Hamiltonian on the circle, you actually have a way to write down the bulk Hamiltonian. That's usually pretty complicated, but you can do that. Then, given such a situation between like the correspondence between the states on both sides, let us think about a feature of such a state. So the specific feature we would like to think about is the so-called entanglement entropy. Now, remember our CFT is defined on a circle. So we may divide the circle schematically into two parts, A and B. Here in this figure, this side is A, and this side is B. Then we can think about computing the Von-Neumann entropy of the reduced density matrix on A for this state. And that is called the entanglement entropy between A and B for this specific state. Now, since we claim a correspondence between ADS and CFT, something which is computable on the CFT side should also be computable on the ADS side. And the question is that how that turns out to be on the ADS side. And that question is answered by Liu and Takayanagi in 2006, where they found that actually the entanglement entropy between A and B is described by something like this, where you have a hyperbolic surface in the bulk, and you look at all the possible surfaces which connects the two endpoints of A. There are many candidates of that. So let us call such a hyperbolic, such a surface gamma A. Then what you are doing is that you look at all those surfaces and you pick up the one which has the minimal area. Then it turns out that the minimal area quotient by some constant is nothing but just the entanglement entropy on the CFT side. And here, this constant appearing here is called the Newton constant, which is a constant characterizing the gravitational theory in the bulk.
The density matrix is infinite dimensional.
Yes, the density matrix is infinite dimensional, but like in, CFT is actually a continuous theory defined on a circle, and the density matrix is infinite dimensional, but there exists a canonical way to do the renormalization to exclude that infinite part from the answer.
So essentially, we're eventually manipulating a finite dimensional part of it?
Yes. So, well, actually, they match even for the infinite part.
Okay.
Like you can not really talk about the infinite part, but you can talk about how the infinite part is diverging and how, like, it turns out the divergent behavior on both sides are also the same. And like so here we look at all the possible surfaces. We pick up the one with the minimal area, and that one is called the RT surface. Okay, so let us we'll get some physical interpretation from this kind of formula. So here we are computing some entanglements on the CFT side, and that turns out to be some geometric quantity on the ADS side. And an interpretation of this is the geometry actually emerges from the entanglement structure of some quantum theory. So this kind of feature is summarized in a pretty much well-known slogan, which is called ER equal to EPR. And the ER appearing here refers to Einstein-Rosen bridge, which is a form of the wormhole in gravity. So that basically means that ER basically means that the spacetime is connected to each other. On the other hand, the EPR here refers to just the entanglement structure of the quantum mechanics. So this ER equal to EPR basically says that geometry actually equals to entanglement. Yeah, please.
So I guess how do you understand, like, what does the Gn in the gravity theory correspond to in the CFT? Because it seems like this quantity goes down when Gn is bigger, which is stronger gravity. So strong gravity means less entanglement.
Oh, sorry. That's a very good point. Yes. So if Gn becomes larger, that means stronger gravity, and stronger gravity from this formula means lower entanglement. And on the CFT side, that is reflected by the local degrees of freedom of the CFT. So you can talk about in CFT, there are two characterizations of the degrees of freedom. So first of all, we are defining the CFT on circle. Then of course, if we define it on a larger circle, it has more degrees of freedom. That's one characterization. And the second is that you can talk about how many degrees of freedom you have on a unit length of the circle. And that's more like a density of degrees of freedom. And that density of degrees of freedom is connected to the 1/G here. So 1/G is basically like a measure of the local degrees of freedom on the CFT side. Thank you for the question. Okay. So now, well, I guess like it might be well known that Einstein didn't actually believe the quantum entanglement. It's like he didn't believe the existence of the EPR pair. That's a pretty well-known story. It's actually less well-known, but also true that Einstein also didn't believe in the existence of the wormhole. So it is a little bit funny that the ER equal to EPR is actually an equivalence between two things Einstein didn't believe. So in that sense, Einstein's belief is like self-consistent. So this is like self-consistent to Einstein beliefs. Okay, maybe let me just very briefly sketch this part. Before we talked about like dividing the whole circle into two subsystems and talking about the entanglement entropy, we can also think about dividing them into more pieces and talk about the fundamental entropy associated to different pieces. And of course, from the quantum information side, we know the fundamental entropy should satisfy the so-called strong subadditivity. And this kind of behavior of the RT formula can be easily conformed by drawing the RT formula and using the triangle inequality in the hyperbolic surface. So in that sense, like the strong subadditivity, which is pretty difficult to prove, like in the quantum information side, is turns into some usage of triangle inequality, which is pretty easy on the gravity side. However, with the triangle inequality, you can also prove some other inequalities between the fundamental entropy. For example, you can prove that the RT formula implies this inequality to be true. This inequality is called the monogamy of mutual information. And actually, this inequality is not true in general quantum manifold system. So this inequality can be regarded as a characterization of geometric state. as we mentioned before, the geometric state is a kind of very special state in the ADS-CFT correspondence. So you can use this kind of inequality to give a characterization of those very special states. And there are actually an infinitely many of such inequalities, which are called the holographic entropy cone. So let us talk about some refined version of the RT formula. Before we found that like the RT formula says that if you want to know the leading order of the entanglement entropy, all you should do is just to look at all the possible surfaces and find the one with the minimal area, and that gives you the entanglement entropy on the CFT side. This leading order means that comes from the smalliness of G Newton, and this order 1 means order G Newton to 0. The initial question to ask is that what should we do if we want to get the order 1 part from the ADS side? So remember that we related a state in CFT to a combination between a geometry and a quantum state defined on that geometry. Yeah, let me use this figure. Like given a surface on this geometry, this surface actually divides the ADS spacetime into 2 parts, where we can call this part EA and call this part EB. Now, given such a bipartition, we can talk about the entanglement entropy between the bulk quantum mechanics here in EA and here in EB. And let us denote that entanglement entropy as this. So it turns out that if you want to know the subleading order of the entanglement entropy, all you should do is to firstly find a surface in the bulk. And then you sum, you take this sum. So you firstly compute the area of the surface, and you also compute the entanglement entropy between the bulk degrees of freedom. After summing them over, you take the minimalization of this sum. So again, like this part is order 1, this part is order 1 over G Newton. So as long as we look at the G Newton goes to 0 limit, this is very large, this is very small. Like the resulting surface of this and the resulting surface of this, they shouldn't be so different from each other. However, they're in general different from each other, and the resulting surface of the later minimalization problem is often called the quantum extremal surface. Okay, so far I have mentioned a very specific aspect of a quantum informational aspect of ADS-CFT, focusing on the entanglement entropy. So actually, there also exist proposals for other informational quantities, such as entanglement of purification, entanglement of formation, and so on. And these kind of things, they also have a geometric correspondence in the ADS spacetime. It is also known that we can regard the encoding map from the bulk to the boundary circle, CFT, as a quantum error correction code in some sense. And that in turn motivates the study of tensor networks using tensor networks as discrete time models of holography. Besides, on the CFT side, because that's a quantum theory, we can talk about the circuit complexity for preparing some states. And it has been conjectured that such complexity for preparing some state can be computed from something like volume or action in the bulk ADS. anything does not really mean anything. It's a name for some quantity. Like some people call something anything, but yeah. Okay, so from this we can say that although I just focus on one specific example, it is clear that the quantum information helps us understand the nature of quantum gravity. From one perspective, the ADS-CFT dictionary has been greatly expanded by the quantum information tools. These kind of developments, in turn, also help us solve some very old but significant problems in quantum gravity. So for example, there is a well-known paradox called the black hole information paradox, which was found by Stephen Hawking back in 1976. And that was recently solved by these people. And what they did is just to apply the quantum extremal surface, which is a quantum version of RT, to a setup with black holes. There also exists like new study in the quantum information discipline, which are actually originally motivated from quantum gravity. So here I gave an example, but let me skip this maybe. Okay, so far we have focused on the informational aspects of the ADS-CFT correspondence. And from now, we would like to think about some computational aspects of the ADS-CFT correspondence. So the first thing we would like to note is that the ADS-CFT correspondence can be considered in some way as a computer. So here the language is not precise, please forgive me about that. But roughly speaking, what we do with that is we can ask a question in CFT, which is a purely quantum mechanical system. And the ADS-CFT dictionary translates that question to some other question, some equivalent other question in ADS. And that question is simulated in the quantum gravity. Then after getting the answer after doing the simulation, like in ADS, you can use the dictionary again to translate the answer back to get the answer of the original question you asked in the purely quantum system. So let us think about this kind of process as a kind of computer. Then some natural question to ask is that what is the computational power of this kind of computer? And given such a computer, is it possible for that to be actually more powerful than a quantum one? And these questions were firstly asked in this seminal paper. Like in this paper, they actually thought about some setup which has nothing to do with entanglement. But let us firstly sketch an alternative version of this, like using the entanglement entropy we just reviewed before. Okay, let us consider the following question. Again, given a CFT state, in the CFT Hilbert space, say we would like to learn the entanglement between A and B for this state. And it is somehow well known that such a learning task is very, very hard in quantum mechanics. And so here by hard, I didn't give a precise definition, but this kind of statement can be made precise via the notion of the so-called pseudo entanglement, which is an application of the pseudo randomness. So, however, let us assume we have access to the gravity dual of the CFT state we just considered here. Then that kind of question of learning about entanglement is translated into a question about learning the area of some geometric surface in the bulk geometry. And such a such a question is like can be done pretty efficiently. I mean, you just like look at the geometry, you find like a surface, and you compute that. So here I just like sketched like a complexity gap between what happens in CFT and what happens in ADS. But for like a more precise setup, please like refer to this paper. Okay, so here in this case, please.
Do we know that the hardness in the first bullet point holds for geometric states?
Yeah, so that, that's a very good point. So here, actually, like did some like cheating kind of thing, because the applicability of the RT formula is only restricted to a subclass of states, which are the geometric state. So I cannot just say, given any random like CFT state, and then talk about the learning entanglement like in that sense. So we should like in some sense focus on just the geometric state, and a precise setup which makes that available is done like in this work. So for specific like setup, please like refer to this.
I have a question over there.
Oh yeah, please.
This complexity gap is just due to the strong weak coupling duality, though, right? Like the nature of ADS CFT in the large end limit. So
yes.
Away from that, do you kind of lose the power of this sort of computer?
Yeah, in some sense, yes. In some sense, yes. And I will comment on that perspective like later.
Okay.
But to be honest, like even for the usual strong-weak duality case, we don't really know from the computational perspective, like what's the fundamental reason which gives us like a easier to compute situation if we have such a duality. So I will mention that later. Yeah, thank you. Okay, so here I use the entanglement to sketch a complexity gap between the CFT and ADS. And actually, the very first example for such a complexity gap was found like in this paper. And the setup they were discussing is based on the circuit complexity for some given state in CFT. So for example, like on the CFT side, which is just a standard quantum mechanics, we can think about the distinguishing task between a random state and a pseudo-random state. And then, of course, it is known that there does not exist any efficient algorithm for us to do that. However, based on a conjecture made by Susskind, the circuit complexity can be at least estimated from the volume of the space. And that turns out to be, again, a quantity which is very easy to be estimated from the geometric point of view. So that can be efficiently done in this case. And from this point of view, again, you have a complexity separation between ADS and CFT. And given such a situation, the BFV paper have argued that such a complexity gap must be due to either of the two possibilities. So the first possibility is that it could be possible that because we use ADS-CFT dictionary in this procedure when translating questions, it could be the case that it's just the ADS-CFT dictionary which is like exponentially hard to be simulated on a quantum computer. So the second possibility is that because this simulating procedure involves the simulation in quantum gravity, so it might be the case that it is actually the quantum gravity part which validates the quantum extended Church-Dillon thesis, which is like a more exciting scenario. And like a fundamental question we can ask is what is the basic mechanism behind, what is the basic computational mechanism behind this ADS-CFT dictionary for which, to be honest, we don't really know the answer. Okay, so given such a situation, and based on the entanglement and entropy we reviewed before, let us give a new twist in this story. So in this kind of discussions, the computational complexity are usually discussed in terms of the system size, n. In other words, you think about you have a CFT, which is defined as a circle. You enlarge the circle size, and you talk about the complexity growth with respect to the enlargement of the circle size. However, as it was asked before, in standard ADS-CFT correspondence, there actually exists another more canonical large parameter which controls the story. And that parameter is the inverse Newton constant, which corresponds to the density of local degrees of freedom on the CFT side. And that is another notion from N. Both of them are some large parameters, but they're different from each other. So given such a situation, it is natural to ask what is the computational complexity consequences in terms of this inverse G Newton from holographic point of view. And another thing we should notice is that, in fact, the validity of the geometric description of ADS, it largely relies on this limit. So we also have looked at the quantum corrected version of the RT formula, where the order 1 correction to the 1/G Newton expansion actually comes in as a computation of the entanglement and entropy in the bulk. So in that sense, although the leading order of that is very easy to compute, in other words, fillable, this order 1 correction is actually unfillable. So in other words, it is actually, in this case, the 1/G Newton goes to infinity limit, which makes the entanglement and entropy fillable. And even in that case, it is only this leading part which is fillable, but not all the entanglement entropy. So this, taking this limit basically separates the system size n out from the story. Yeah, please.
Wait, sorry, does fillable just mean efficiently computable in the ADS theory? Or?
Yeah, sorry. This fillable means efficiently simulatable on a quantum computer. Yes, sorry. Okay, so then a natural question to ask, where I don't really have an answer, is that if there exists a fundamental mechanism behind this kind of phenomenon, so maybe it can imply the possibility of the existence of a class of efficient algorithm for evaluating only the leading order of some quantities. And that may lead to something like holography-inspired quantum algorithm. And also, as commented before, this kind of phenomenon actually does not only happen in the ADS-CFT correspondence. It happens in a pretty large discipline in theoretical physics, where if you have some large number in your theory, in some cases, this large number helps you to turn a very complicated computation into a very simple computation. That is by experience the case, but we don't really know what's the computational theoretical reason behind that kind of phenomenon. So it would be great to understand this kind of thing. Okay, since the time is approaching, let me make some concluding remarks. So here we have reviewed several informational and computational aspects of holographic principle using mainly the ADS-CFT as a working example. There are many different information theoretical perspectives of ADS-CFT, but we focused on entanglement as a guideline. So we have seen that via holography, the tools from quantum information has greatly improved our understanding of quantum gravity. So it has a very great impact on the physics point of view. On the other hand, these days, the quantum gravity has also started motivating new study in quantum information. And by regarding the ADS-CFT correspondence as a computer, like arguments from a theoretical computer science point of view turns out to be useful to give us like an understanding of the ADS-CFT dictionary from another very different point of view, and that is expected to have great impacts on quantum gravity. Okay, as the very last thing I would like to mention, which I also mentioned at the beginning of this talk, it is always the case that implementable computational models are built on some physical reality. Like we can talk about different theoretically like computational models based on bits or qubits or some other like quantity or some other fundamental structure to do the computation. But it's always the something which has a foot on the physical reality, which makes it implementable. And again, like in our universe, we have gravity as a part of the physical reality, and that part has not yet been used to build a computational model. So it would be like really great to come up a way to try to build a computer based on that. And like, well, it could be the case that such a computer has no difference like from a quantum computer. That would be the most disappointing scenario. But it'd be like really interesting to understand how powerful such a thing is. And I would like to end here. Thanks for listening.
So I have a question. So I'm kind of confused by when you were mentioning that some problems are hard fundamentally but easy after we use ADS-CFT correspondence. Is it because essentially we have this gravity computer and those problems are easy in the gravity computer complexity?
Yeah, so good point. So I actually like mentioned some of them like here. So like the answer to that question is that we don't really know what's the fundamental reason which makes the thing easy on one side and hard on the other side. It could be either like the dictionary itself is very, very complicated, so it resolves some complexity when translating one problem to the other. And it could also be that like when you use quantum gravity to simulate your problem, it's fundamentally more powerful than a computer. But so far, we don't really have a good example to separate them from each other.
If essentially ADS-CFT eventually turns out to be correct, would that like be an attack on the proofs that those problems are hard, or?
Yes, like if you like imagine you have a full accessibility to the full ADS-CFT dictionary, then definitely you can evaluate how powerful that dictionary is. Then with that, you can talk about like which part of the problem is can be like accelerated by using this kind of mechanism, which are some like more boring question which you cannot do that. Yeah.
Are there holographic correspondences besides ADS-CFT?
Yes. So the ADS-CFT is the most well understood example in the sense that it has many different formulations, and they all agree between each other. So the ADS-CFT correspondence was originally found actually in string theory, but as you can notice, like all the things I mentioned, I didn't really mention like anything from string theory. actually, it can be also defined outside of string theory using something called gravitational path integral. And there are like different formulations, but you can compute from both sides, and you can find agreement between them. And that makes, getting ADS-CFT correspondence from a different perspective makes it like a pretty well-established correspondence. Like we can also get some other kind of correspondences by generalizing the way how we get the ADS-CFT. But those models are relatively not so well established compared to ADS-CFT. But yes, they exist. Yeah, please.
So this result gives us that if if this ADS-CFT dictionary is like efficiently computable, then like quantum gravity and ADS quantum mixed energy trajectory. Does that necessarily do we believe that this extends to if we were to actually implement a quantum gravity based computer? Do we believe that this extends to our universe, like the De Sitter space?
So I think that's an open problem.
Yeah.
Yeah, and we don't really have an answer to that question, and different people may have different opinions. But I personally, I think that should be possible. Because although such kind of arguments, they are pretty much based on ADS-CFT correspondence, but there are certain flavors which are not unique to ADS, but also to our De Sitter universe. So it might be a way to get around from ADS-CFT and only use some more minimal set of assumptions to try to build such a thing. Please.
Can I think of how you can formalize the computational model of what observers can do on the ADS side? And one way I can think of is assume you have an oracle that can, say, do what observers on the ADS side can do, like maybe measure areas, volumes, basically. But maybe they can only do that to some additive error, because otherwise you are kind of feeling the unfeelable.
Yeah.
Are there other primitives, computational primitives, that observers on the ADS side can do that we do not know how to efficiently describe or simulate on the CFT side?
Yeah. So far, the major examples discussed here are the computational complexity and the entanglement. But
so they both relate to area or volume.
Both are related to area volume, but there are certainly some other examples. For example, you can easily extend this kind of arguments to things called Wilson line or something like that. And from this procedure, it's just as you mentioned, it's sounds very reasonable that somehow someone who knows gravity as at the very beginning serves a kind of more powerful version of merging in the interactive formulation of a computational question in this kind of setup. But how to make that precise, so far I don't think anyone has a very good idea. Yeah, there are words floating around saying, oh, gravity as an oracle, black holes as an oracle, but so far no specific formulations.
Any other questions? Thank you.
Thank you.